1 on Fourier series. This chapter is on Fourier and orthogonality. So we'll do Fourier series, Fourier transform on lectures 6.1 and 6.2. And then we'll also do a discussion of orthogonality, which is one of the properties that the Fourier series has. And this property becomes particularly useful to us when we go to solve partial differential equations. And when we solve partial differential equations, one of the methods we'll use is, the primary method we'll use is going to involve the Fourier series / transform. So that's why we're going back through that. It turns out that you can also solve partial differential equations with other types of functions that all have in common that they are orthogonal. Okay, so orthogonality is a larger class of things than the Fourier series and Fourier transform. There's also like the Bessel function and another one that I can't remember off the top of my head. Legendre polynomials, I think. Yeah, and there are others. So it's pretty fun. So we'll start out, though, with hopefully somewhat familiar territory for you, the Fourier series. Great. So Fourier series are mathematical series that can represent a periodic signal as a sum of sinusoids at different amplitudes and frequencies. They're useful for solving for the system of the response of a system to periodic inputs. However, they are probably most important conceptually. They are our gateway to thinking of signals in the frequency domain, that is, as functions of frequency, not time. To represent a function as a Fourier series is to analyze it as a sum of sinusoids at different frequencies, omega n, and amplitudes, an. Its frequency spectrum is the functional representation of amplitudes versus frequency. Let's begin with the definition. The Fourier analysis of a periodic function y is, for n being a natural number including 0, period t and angular frequency omega n, given in 6.1 and 6.2. So we integrate the function over a single period with a multiplication of the function in the integrand as a multiplication of it with cosine in the an case and sine in the bn case. You can actually take the integral over any period. The integral shown here is from negative period over 2 to positive period over 2. The Fourier synthesis of a periodic function, y, with analysis components an and bn corresponding to omega n, is given in 6.3, which is an infinite sum of the an and bn coefficients multiplied by cosine and sine. A0 is just 6.1 with n equals 0 plugged into it. Okay? So that is that. Sometimes it's given as a separate formula, but it doesn't have to be. Let's consider the complex form of the Fourier series, which is analogous to definition 6.1.1. The Fourier analysis of a periodic function y of t is, for n, a natural number including 0, period t and angular frequency omega n, Cn is this integral, is a single integral now of y with the exponential. Now it's a complex exponential, but it's a single integral, and using an exponential in your integration is usually much easier of an integral than using cosine and sine. At least for my money, I'd rather have an exponential in my integral than having a trig function, because who wants to do those trig identity integrals? Not me. But I'll just use sim pi to do it, so whatever. The Fourier synthesis of a periodic function y with analysis components Cn corresponding to omega n is given by the sum. So you analyzed it into these components, and then we're going to sum it back up to get the original signal again. And I'm not proving that you get back the signal. There are all these conditions for getting back the original signal, but if you have a periodic function, you can get actually an exact replication if you take the infinite sum of the input signal. The only difference is that if you have discontinuities in your periodic signal, so for instance, if it goes from like high to low with a jump, the Fourier synthesis will actually, instead of having like a value of one of the endpoints or no value there, it'll be it'll be defined at this transition as the mean of those two endpoints. So that's the only difference between your signal. So you can essentially perfectly reproduce every periodic signal with this. It's pretty cool. As long as it's continuous. Or not continuous, as long as it's defined everywhere. So as long as it's piecewise defined on the entire axis. We call the integer n a harmonic of the frequency associated with it. So omega n equals 2 pi n over t, the harmonic frequency. So it could be the first harmonic, second harmonic, third harmonic, etc., depending on what n is. So if n is 1, it's the first harmonic. If n is 5, it's the fifth harmonic. There is a special name for the first harmonic called the fundamental frequency. It is called this because all other frequency components are integer multiples of it. Okay, so if you keep increasing n here, these are integers, and I'm going to multiply that initial one by 2, 3, 4, 5, etc. So that fundamental frequency is especially interesting to us, and in many cases, that fundamental frequency will have the largest component associated with it. So it's the magnitude of Cn, or the magnitude of the combination of An and Bn will be largest for that fundamental frequency. It isn't always the case, but it is frequently the case. Okay. Good deal. It is also possible to convert between the two representations above. So, for converting between the forms, the complex Fourier analysis of a periodic function y of t is, for n being a natural number including 0 and an and bn as defined above, you can get Cn by essentially just combining the ans and bn's as being real and imaginary parts with an appropriate factor there. The sinusoidal Fourier analysis of a periodic function y is, for n and c above, you can go from c to an and cn to bn as well. So that's how you go in between the two. So sometimes it might be better to go with the trig form, or more frequently it's better to go with the complex form for doing the integral, and then you can convert to the other type if you wanted to. There's no real reason to, in most cases, convert, but you can, and it's nice to know the equivalency.
Is in 6.8 and 6.9 where the second term is c sub negative n, is that like approaching c from the negative side of things?
No, so we actually had negative indices in the 6.4 here. So for the complex representation here, we have, so n equals 1, n equals minus 1, n equals 2, n equals minus 2. So there's a c minus 2 component as well. So there you get the harmonics in positive and negative. So that's what that subscript means here, is you take the negative component. So if you want an, you just add these together, the symmetric c's. So one side will have a cn, and then there'll be a c minus n, and when you add them together, you add the real parts and you add the imaginary parts, and you get back a real number. So those imaginary parts are going to go away, right? So they have to sum to 0. Yeah. Very good. The harmonic amplitude is given by equations 610 and 611 for the complex form. For an and bn, it's this root sum square. Yeah?
So maybe I don't understand this, but so for the natural, like, what is a negative natural frequency? Like, is that, it just doesn't make sense.
Yeah, so negative frequencies are mathematically convenient, but they don't have a real physical meaning other than like a reflection of the positive frequency. So you'll see negative frequency show up in Fourier integrals, and there you can take the one-sided transform, the two-sided transform, all that. We'll talk about that when we get to Fourier transforms. But it's important to realize that those are just mathematical niceties. When you get down to the final equation, if your function is a real function, y of t, all those complex numbers and all the negative frequencies will not be a part of the final representation. Yeah, or at least there is a way to represent it in completely real components at the very end. So just like when we have complex numbers that describe like our AC electronics circuits, like we've got using phasor notation. Well, the complex representation corresponds to some real quantity that we're representing in this complex way. So when it gets down to like an actual frequency, it's going to be only real values, or only positive values for frequency. Yeah. So, yeah. A line spectrum is a graph of the harmonic amplitudes as a function of the harmonic frequencies. The following illustration demonstrates how sinusoidal components sum to represent a square wave. So we've got the amplitude vertically here. We're looking at the fundamental frequency sinusoid with the large amplitude here to represent this square wave. So we're doing a Fourier analysis of a square wave, but we're going to sum up all these sinusoids to get us approximately to a square wave. You'd need all of them to get perfectly to a square wave, and then still the discontinuity would have the discontinuity would still have like the average value. So it's not exactly the original function because of that, but it's very, very close, right? We see here that on the spectral amplitude line, as you increase in frequency, the amplitudes are dropping off. So you can think of these spectral amplitudes as being like the projection of this sinusoid onto this axis here. So we're like projecting this way. So you see that these small amplitude and higher frequency components are represented on the spectral amplitude as being smaller. So this sum gives us what's starting to look like, even after 1, 2, 3, 4, 5, 6 non-zero terms, we're getting something that looks like a square wave when we sum them up. So you can do this as a way of approximating a function using sinusoids, and just take a partial sum of the sinusoids that represent the Fourier series. And in the limit, you have a solution. So, or in the limit, you have the entire signal. That's actually, we're going to use that mixed with the principle of superposition to do things like finding the response of a dynamic system to a periodic input. It's not a sinusoid, it's like a square wave or something. So you can use Fourier to do that. We will use a similar concept to do partial differential equation solution. So that's kind of where this is headed. Is next chapter we'll learn how to use this Fourier series to do solutions to PDEs. But you can do it for ODEs as well, and we've done that. If you in the system dynamics class, for instance, we used Fourier series representation to do that. Okay, so compute in this example. Compute the first 5 harmonic amplitudes that represent the line spectrum for a square wave in the figure above. So this is the square wave. If this is the origin, t equals 0, then it has this value, call it 1, amplitude 1, etc. Then it just repeats, right? So this is the time domain, and this is the amplitude. So we'll say it has amplitude A, and it has period t. And we want to compute the first 5 harmonic amplitudes. So go ahead and start trying to work on this. I'll come back in a couple minutes. I'll stop the video and then do a second part for the example.